In this session, we're going to be looking at the principles of starting to build a model in quantum mechanics, and in particular we're going to be focusing on kinetic energy. So in chemistry we think of four main levels of energy. We think of translations, rotations, vibrations, and electronic transitions. We're going to go through all of these in turn in quantum mechanics, but to start off we're going to look at translational motion. It's a fundamental consideration in quantum mechanics and concerns the application of kinetic energy. So in a classical system, kinetic energy can have any value that we consider. So we have this continuous variation throughout. However, as we've already seen, in quantum mechanics, we need to quantize those energy levels. So what we need to do is we need to come up with a thought experiment on how we explore these. And a particular thought experiment we consider in quantum mechanics is that of the particle in a box. It sounds slightly odd, but we consider what happens to a particle when we put it in a bounded region. So at first we're only going to consider one dimension, and this is the particle in a one-dimensional box. We'll deal with other dimensions later on, but first of all we'll just consider the single dimension for simplicity's sake. So we have to first picture this particle in the box. The particle can move freely in that single dimension. So if we have a single dimension here, our x dimension, that particle can move freely in that space. We then need to set the rule that the particle can't move outside the box. So we set boundaries at one end and the other end of that box. One classical image of this that you might like to think of is a bead on a string. So if we have a string, and we put our bead on that string, it can move freely along that string, but it can't come off the end. Importantly, the string is horizontal, so there's no potential energy to consider. All we care about is the kinetic energy. Kinetic is the only form of energy that matters, and for the sake of argument, we ignore friction. In the quantum mechanical realm, there is no friction. Okay, so that's a bit about the particle. Let's look at the box. We're only going to consider a single dimension now. We're going to consider the x dimension. We'll add others as our understanding develops. So we pop our particle in this box, and the particle is bounded by something called potential barriers. So what we're saying is outside the box, the potential is infinite. Remember our restrictions on the wave function, that at an infinite potential we couldn't have the wave function, it would have to be zero. Inside the box, the potential is zero. And this means that the only energy we worry about is kinetic energy, as we've already said. Finally, we say how long the box is. The box has length L. Just for the sake of argument, it could be whatever length we want, but we can plug the value in when we actually do our calculations. And x here is the coordinate system we're working on. So when we look at the wave function varies as x varies. So it is a function of x. Okay, let's look at the particle. That particle, remember, its behavior is described by its wave function, and that wave function is currently in the x direction because we only care about one dimension. It has this symbol, psi x. And, as we said before, psi x is a function of x. Just says it varies as x varies. We now need to look at these boundary conditions. Remember, we said that the wave function is zero at infinite potential, and as a result, the wave function has to be zero at the edge of the box. For a number of reasons, one of which is, remember, the wave function has to continuously vary, so it has to come smoothly down to zero for when it leaves the box, but also the uncertainty principle says at the edge of the box we know exactly where that is, so we can't know anything about the particle, so it can't exist there either. So we look at this first wave function. Well, we have a wave. It's inside our box, between 0 and L. Is this a valid wave function? Well, first of all, it has to come to 0 at the edge of the box. So here, it doesn't come to 0. So this is not a valid wave function. Let's look at another one. Well, here we're at 0. The wave moves through the box, but the wave function again is not 0 at the other side. So we have to tie it to 0 at both sides of the box. And this means that the shape of the wave function is particularly confined. So it has to be at 0 and those points are locked in. Inside the box, the particle travels to the edge and then turns around and comes back. And the overall wave function that we see is the sum of the forward and back wave functions. Let's now consider the energy inside our system. So look at our Schrödinger equation. If you remember, our Schrödinger equation looks like this. Now remember, our potential term, this part here, goes to 0, so we don't need to worry about this. So we only consider the kinetic energy here, the double differential, or the second derivative, and we're considering it in a single dimension, in x, which means that the equation simplifies to this form. So what is this equation telling us? Fundamentally, it's telling us that we need a function, our psi, as a function of x, we need a function which, when we do a double derivative, so when we find the second derivative of that function, we get the same function out again multiplied by constant e. And this is how these differential equations work. It's worth putting a quick aside in here to talk about eigenfunctions. An eigenfunction is simply a function which relates to itself. So this eigenfunction means itself in German. So we have an eigenfunction, which is our wave function here, and we have an eigenvalue, which is this e term. The eigenfunction is a function which is scaled and returned when passed through an operation. So whatever operation we do, that eigenfunction is scaled and returned. So we get the same function back multiplied by a constant. That constant is the eigenvalue, that scalar value that multiplies the eigenfunction. So if we passed our function through here, we would get a constant times our original function. There's a practice exercise that you can do, so pause the video if you want to work through this. So we're going to assign a function here, just a random function, just pull it out, 2 psi squared plus 4 equals e psi. So this is an eigenfunction equation. So what you need to do is identify the values of psi, which are eigenfunctions of the above operation, and for each eigenfunction determine the corresponding eigenvalue. And here we're only going to let the eigenvalues be integers, be whole numbers. So for each of these, let psi equal a particular value. A worked example here, let psi equal 1. So let's take psi into this equation. 2 times 1 squared gives 2, plus 4 gives 6. Okay, how does that relate to the original function? Well, 6 is 6 times 1, which is 6 times psi. So 1 is an eigenfunction of that equation, and the eigenvalue is 6. So have a go working through all of these and decide which ones are eigenfunctions in these settings. So when we talk about solving the Schrödinger equation, we simply mean finding the functions that fit into this differential equation. So when we look at this equation, there are several functions that will fit in to provide a potential solution. The first one is e to the kx. So if we take the second derivative of this function, what we find is we end up with the original function returned multiplied by k squared. Make sure you're happy with these results. Make sure you can follow through the differentiation to get to these end results. And if we look at it, we have a constant, k squared, times the original function, a e to the kx. Another function which fits this bill is the cosine function. So when we take the second derivative of this, we find that we get minus k squared times the original function. And again, the sine function, in much a similar way, would return minus k squared times the original function. So which one do we use? Well, what we need to do is we need to look at the boundary conditions of our box. Remember, our boundary conditions say that at the edges of the box, where x is 0 and x is L, the wave function must be 0. So let's let x be 0 and calculate the value of psi for each one. If we start with a e to the kx, stick 0 in there, we end up with e to the power 0, which is 1, multiplied by a. So when x is 0, the wave function is equal to a. That's not a 0 wave function, so we can't use this wave function. Look at the sine function now. Well, we now have sine of k times 0, sine of 0. Sine of 0, by definition, is 0 times a gives 0. This is an allowed wave function. Let's now look at the cosine function. A times cosine of kx, cosine of 0, gives 1. So we end up with a non-zero wave function. So only one of these fits that boundary condition. So now that we know we're looking for a sine function, let's try and visualize it. Let's try and fit it into our box. So we're going to picture the box. Remember, the potential is infinite outside, and we're going to fit the sine function into the box. Remember, it has to be 0 at the edge of the box. This dotted line just represents the 0 line for that wave function. And we can see we fit a sine function in straight away. Remember to pay attention to the boundary condition. Remember, we can't have it at non-zero values at the edge of the box, so only certain wavelengths will fit in there. Is there a pattern to these wavelengths? Well, let's have a look. Let's start trying to fit them in. Anywhere we pin the wave function to 0 at the edges, can we fit this in? So it turns out there are different wave functions we can fit in. Here, we're still at the 0 line at the edges, but our wave function still fits in, but it's a different wave. We have a different frequency. So how do these frequencies relate? And what fits inside that box? Well, we've got one wave here, and if we consider what the wavelength of this wave might be, well, if we look here, we've got a half wavelength where it returns to 0, so the wavelength must be twice the length of the box. For a second one, we now have a full wavelength, so we have 2 half wavelengths fitting inside the box. Remember, a sine function after every half wavelength it returns to 0. So we're looking for multiples of half wavelengths. And sure enough, when we look at the third one, we have 3 half wavelengths. So let's reason through the mathematics to try and find out what the value of k is in this sine function. So let's look now, instead of considering what happens at x equals 0, let's think what happens at x equals L. Well, at x equals L, sine KL equals 0. So now we think, what values of KL will give a sine of 0? Well, 0 will. We know that one. But then we think, well, okay, sine of pi gives 0. And sine of 2 pi gives 0. And sine of 3 pi gives 0. So we're looking at multiples of pi. So this will carry on going. Remember to work in radians in this situation. So if we're saying that KL equals 0 or pi, or 2 pi, or 3 pi, and this will go on forever. Remember, it's a cyclic function. That means we can rearrange this to say that k is equal to 0, pi by L, 2 pi by L, and so on and so forth. Notice we're counting up in integers. So we can replace our integer with the number n. So we say k is n pi over L, where n is a positive integer. We can then put this value into our wave function, and we get a wave function of sine n pi by L times x. To summarize everything we've covered so far, translational motion involves kinetic energy, and it only involves kinetic energy. To explore this, we've bounded a particle in a single dimension, and we're keeping that model deliberately simple. We're not wanting to look at potential energy at this stage because it compounds things. For this, the Schrödinger equation can be solved. What that means is we found a function which fits into that differential equation. We find that Eigen function, that function which returns itself when passed through the operation. And from the boundary conditions, we can find the value of k.